Hello and welcome back. In our previous examples of work and energy so far, when we applied a force, it was usually canceled out by another force, balanced out by another force, such as gravity or an elastic object or friction. If we do work on an object and that force isn't canceled out by another force on that object, then the object accelerates. So that work becomes a different type of energy. And the type of energy that it becomes is kinetic energy. And I'm sure you've heard of kinetic energy before, the energy of motion. So what sort of things would affect how much kinetic energy an object has? Okay, I think we would agree that in terms of kinetic energy, the object up top had more kinetic energy, and it had more kinetic energy for two reasons. One is it was moving faster, and two, because it had more mass. Okay, so those are the things that should probably be in our kinetic energy equation, and they are. So Ke, or kinetic energy, equals mv squared over 2. Mass times velocity squared divided by 2, or 1/2 mass times velocity squared, however you want to say it. So that is the next equation that you're going to want to have familiar to you. We'll be using that equation several times. All right. So which has the bigger effect on the kinetic energy, the mass or the velocity, or is it the same based on the equation? Well, since the velocity is squared and the mass is not, it ends up that the velocity is going to have a bigger impact because there's two velocities essentially that are impacting the kinetic energy. So, and it does have a bigger impact. So, if you have two objects, one that are traveling the same speed, one has twice the mass. Okay? If I double the mass, what's that going to do to the kinetic energy? Well, that's going to double the kinetic energy. So the one that has twice the mass has twice the kinetic energy. Okay. Now, if I have two objects that have the same mass, but one has twice the velocity, okay, well, if I double the velocity and then I square that, what's going to happen to that 2? Well, it's going to square into a 4. So if I double the velocity, I'm going to have 4 times the kinetic energy. So again, that's where that squared factor comes into play, 4 times as much. And there'll be some questions along those lines on the test, as usual. So number 5, or just a question, what is the kinetic energy of a 2 kilogram object if it's moving at 3 meters per second? And what is the kinetic energy if it's moving at 6 meters per second? Well, if it's moving at 3 meters per second, we take our mass, 2 times 3 squared divided by 2, and we get 9 joules. Okay. If we double the velocity, instead of 3, it's moving at 6. Okay, we have 2 times 6 squared divided by 2. That gives us 36. So notice when we doubled our velocity, the kinetic energy quadrupled, 4 times as much. Okay. How much kinetic energy does a 23 kilogram object at rest have? Well, what does at rest mean? It means that it's not moving, which means that the velocity is 0. So if the velocity is 0, it doesn't have any kinetic energy because anything times 0 is 0. Okay. Don't confuse kinetic energy with momentum. They both have mass and velocity in them, but kinetic energy is mass times velocity squared divided by 2. And momentum is just mass times velocity. They can both be conserved. We'll get into that a little bit later. So how would it be possible for a mouse and an elephant to have the same kinetic energy? I'll give you a hint, there's actually 2 ways. All right. One is if the mouse and the elephant are both stationary, they both have 0 joules of kinetic energy. Or 2, if the mouse is moving very, very quickly and the elephant is moving very, very slowly, they could also have the same kinetic energy. How much kinetic energy does a ball have sitting in your hand? If it's just sitting there, how much kinetic energy does it have? Well, you'd be tempted to say 0. Okay, but let's pretend that you were actually sitting on an airplane and you and the ball were traveling very, very fast. Okay. It ends up that since velocity is relative, the ball doesn't have any velocity relative to the plane, and therefore it wouldn't have any kinetic energy relative to the plane. but compared to the ground, it's got quite a bit of kinetic energy. So because velocity is relative, so is kinetic energy. Just kind of a side note to keep in the back of your mind here. So sometimes when we add energy to a substance, the temperature goes up. It increases in temperature. And what type of energy does the temperature increase? Well, what happens to the atoms when the temperature of a cup of coffee goes up? Okay, they start moving more quickly. So if the atoms move more quickly, okay, when the temperature increases, that means that we've gained what type of energy? We've gained kinetic energy. Okay, so temperature indicates the kinetic energy of the atoms of a substance. So that's also something to keep in the back of your mind. Moving atoms have kinetic energy. The higher the temperature, the greater their kinetic energy. Okay. So the work done on an object, if it doesn't go into another slot, that work done is equal to the change in kinetic energy. So how much kinetic energy will an object have if it starts from rest and 150 joules of work are done on it? Well, assuming that energy doesn't go anywhere else, it'll all go into the kinetic energy basket, and it'll have 150 joules of kinetic energy. And we'd have to specify a little bit more about that. Okay, this looks like a multiple choice question you might see on a test. 100 Newton force is applied over 5 meters to a 1 kilogram car at rest and to a 2 kilogram car at rest. Okay, afterwards, which car has more kinetic energy? Well, this is a complicated question and a very simple question, all at the same time. Okay, so one thing we just said is that if we want to figure out the amount of kinetic energy they have, we would want to know the amount of work done on each. Well, if each had 100 Newton force applied for 5 meters, each is going to have 500 joules of work done on them, which means they're both going to end up with 500 joules of kinetic energy, assuming the energy doesn't go somewhere else. Okay, so that answer is the same. Okay, now which car is moving faster? Okay, well, if they both have 500 joules of energy, the lighter car has got to be moving faster in order to have the same amount of kinetic energy as the heavier car. Or if you push on it with the same force, the 1 kilogram car is going to accelerate more quickly. So 2 ways you can answer that question. So objects with kinetic energy, any object with energy can do work. Energy is the ability to do work, but objects with kinetic energy can also do work. Okay, an object that's moving can hit another object, push on it, and make it move, thusly doing work. Okay, so and that work is done against friction and gets converted to heat and doesn't get stored as something else. So assuming the crate comes to a stop. So the more kinetic energy an object has, the more work it can do before coming to a stop. Okay? So the change in energy equals work, or in this case, the case that we're going to be talking about, the change in kinetic energy is going to equal work, or 1/2 mv squared equals force times distance. Okay, so the kinetic energy of the object is equal to the work done to bring it to a stop. That is true. Okay, so if we have a car and it drives into a spring, okay, it can store that energy in the elastic potential energy of the spring. Okay, as the wagon loses energy, the spring gains it, and that energy just changes form, and we'll get more into that a little bit later on. Okay, again, and in the process, the spring does work on the car and changes the energy of the car. So work equals the change in energy. We're just trying to beat that into your brains a couple more times. So we've got a car that's moving at 5 meters per second. It's 10 kilograms. What's the car's kinetic energy? How much work would have to be done to stop it? And how far will the object travel if the stopping force is 10 newtons? Okay, well, first off, let's figure out the car's kinetic energy. Well, Ke equals mv squared over 2, the new equation we just got. So m is 10, 5 is v, and that gets squared, divided by 2, so that's equal to 125 joules. Okay, so the car has 125 joules of kinetic energy. We're going to, in order to bring it to a stop, we're going to have to change its energy by 125 joules. So then that's the work that we need to do to stop it, because work equals the change in energy. So how far will that car travel if the stopping force is 10 newtons? Well, we know we're going to do 125 joules of work, okay, in order to bring it to a stop, okay, and that equals force times distance. Our force is 10 newtons, and distance is what we're trying to find, so the distance is going to equal 12.5 meters. Okay, and all we did was set that the work of 125 joules equal to force times distance. And plugged in 10 for the force, because that's what it gives us. Okay, so now let's look at stopping distances. So the more kinetic energy an object has, the more distance it's going to skid before it comes to a stop. The more work that's going to have to be done on that distance of skidding. Okay, so an object that's moving at 10 meters per second, let's say, skids for 1 meter. Okay, an object that's moving twice as fast, how much more kinetic energy does it have? Well, if it's moving twice as fast, it's got 4 times, because remember the velocity is squared. It's got 4 times the kinetic energy. That means it's going to skid for 4 times the distance. Okay? And an object that's moving at 40 meters per second, okay, so it has 4 times the kinetic energy, or I'm sorry, 4 times the velocity. It's going to skid for 4 squared times the distance, so 16 times as far. So that there sometimes is a question on your driver's license exam along these lines. Whereas if you're traveling twice as fast, how many times more do you skid? So now you'll at least have seen it in physics as well as in the booklet. So keep that in mind when you're driving. When the faster you're driving, it exponentially increases the distance that it takes to stop. Okay, so what I'd like you to do is do worksheet 6-3. Make sure you show work, and good luck.